the dark sector. This is where we house the South Pole Telescope and also Bicep 3, another telescope. Here's the primary dish you can see here. And we're currently doing a little bit of calibration, so it's going to turn in a little bit. And to the left you can see the receiver cabin. That's where we house all of our sensitive electronics, our main camera that's imaging the sky. So we're collecting light up from the sky in the primary dish, and then it's getting collected inside the receiver cabin.
Before I show you the telescope, I think it's important to talk about what it's looking at. It looks at the sky differently than what a telescope in your backyard. That telescope looks at visible light. The South Pole Telescope instead looks at microwave light, which is invisible to our eyes, but is everywhere in the universe. In particular, the telescope is designed to observe the cosmic microwave background, or CMB. The CMB is important. It's one of the strongest pieces of evidence that we have that the Big Bang actually happened. Soon after the Big Bang, the universe was full of hot plasma. Some people call it a soup of energetic particles. Within this soup, light couldn't travel very far. The soup was opaque. Finally, after about 300,000 years, the universe expanded and cooled enough that light could actually travel through it. And the image that we see today is a snapshot of that moment in time, which we call the cosmic microwave background. So basically, if you were to write a book about the universe, the cosmic microwave background can take us all the way back to chapter 2, but it can also give us clues about chapter 1. So back to the telescope. The biggest part of the telescope is the primary mirror. This is what gathers the light from space, and it reflects it toward the secondary mirror. The secondary mirror reflects toward the tertiary mirror, which then sends the light down through some focusing lenses into the camera. The camera itself is made up of 16,000 individual pixels that are very sensitive to microwave light. Each pixel is actually a microscopic superconducting material whose electrical properties are very sensitive to the incident heat or light that hits them. This is a simplified version of what happens inside the telescope. Occasionally, these components need to be checked or have parts replaced, and to do that, the telescope is rotated and tilted so the receiver cabin rests just above the building. Then, we open a hatch in the roof of the laboratory to access it.
So this is the receiver cabin. Here's the axis of the telescope, the azimuthal axis, so it's what it turns left and right on. We're going to open these doors in a second and get inside. There's a bunch of optics and cryogenic equipment in there that we need to investigate. We're up inside the receiver cabin, and this is our receiver, so all of our cryogenic electronics, all of our detectors. This is the camera that's looking at the sky. This is the camera box, and there's the optics pointing up, and there's some mirrors. This big oval here is the secondary mirror that's pointing out to the sky and looking at the big primary dish that you can see on the walk over here.
Remember how I said that the cosmic microwave background, the CMB, is the first light we can see from the early universe? As the universe expanded further, the CMB was stretched and weakened. Whereas it was bright in the early universe, now it's pretty faint. It's so faint that any other heat or light will overload the telescope's camera and make seeing the CMB impossible. The telescope's imaging camera has to be kept very cold. In fact, it has to be kept a fraction of a degree above absolute zero.
Here we're standing right underneath the telescope. This is a big ass bearing that the whole thing is spinning on. We're standing underneath 350 tons of metal. And here we go, now we're moving around. And inside the housing here, there's 2 elevation arms with motors that allow us to tilt up and down.
The South Pole Telescope is also part of the Event Horizon Telescope Network. This network connects the data from telescopes around the world to image really small objects, most famously the supermassive black hole at the center of the M87 galaxy.
During our season, the Event Horizon Telescope Network studied the supermassive black hole at the center of our own Milky Way galaxy, and now, at the end of winter, Sasha has to pack up all the EHT hard drives to send back north for analysis. Upstairs, there's one last piece of hardware that I think is cool.
This is a hydrogen maser atomic clock. This atomic clock helps keep very precise time for all the data, so when they match up the data later from all the telescopes, it all syncs up.
Upstairs is also where we make our coffee and our tea after the long walk out, and you can admire the telescope while staying cozy and warm. If you haven't seen them yet, check out my full interview with Sasha, and also the full walk out from the station to the telescope. Well, we better head back to the station before the weather turns. This is Joe Spins the Globe, and I'll see you around the world.